the simple equilibrium, if you will, determining equilibrium constants for your individual acid-base reactions, the pH calculations and pOH calculations. Okay? So it's just looking at those interrelationships. So a lot of the calculations that you'll see both in the homework and things that I'm going to attempt to go over for examples in our lecture are just looking at those kind of interconversions. We tie that together with the equilibrium that we already looked at, and so you're now compounding the amount of work that you do, but it's hopefully just a couple extra steps. Hopefully it's not too conceptually difficult as far as the calculations go. Okay? Today, we're going to get into some of our definition issues with acids and bases and how we can avoid the mathematics and try and come up with some interpretive abilities, okay? Which will become more handy when you get into organic chemistry, and they'll go through the definitions again then. But that said, students are typically still very, very weak with your acid-base definitions, even in organic chemistry. So if we can put an emphasis on it now, hopefully that'll carry over well, and it won't be as big of an issue for you. Okay? It's also the most applicable thing that you pick up out of this course. Okay? So with our acid-base definitions, so the ones that are primarily important are your Bronsted-Lowry definitions. So we're looking for that hydrogen ion exchange. Okay? And then we said strong versus weak. Okay? The strong acids you said you had to have memorized, so we've got those six strong acids that I want you to have memorized. And then your weak acids and bases is pretty much everything else. Okay? So when we go through and look at those, that's going to be kind of the crux of a lot of the homework problems, is looking at how those weak acids and bases determine different equilibrium constants and concentrations, and then ultimately what can we do with those weak acids and bases, which really shows up or really becomes a big impact when you move into biochemistry and you're looking at, or even biology, biological systems and buffer systems. Okay? The reason we exist in the environments we do is because our blood is buffered at a certain pH. To do that buffering, we have to have a weak acid-base equilibrium within our blood. Okay? And that actually has all sorts of other effects that we take advantage of as well. Okay? So it is really important to kind of evaluate these buffer systems and see what's happening. Okay? So the first thing I kind of want to get into, though, is the more fun stuff, is looking at structures and trying to determine whether it's a weak acid or a weaker acid. So trying to evaluate without numbers what's happening with the overall chemistry. And the example that we looked at yesterday was I drew up two possible species. We had, what did I have? HX going to H plus and X minus. And then I said HY plus going to H plus and Y. Okay. And I picked this to say, as a first approximation, we might suggest that HY plus is more acidic than HX. And that's because when we look at the products, when we look at how those two species act as acids, they both generate H plus, which means they're both generating some kind of acid. We want to know how much acid they produce. Okay, so we could go through the mathematics and determine it, but that's a bit difficult. So what we'll do instead of looking at the mathematics is look at what else is produced in that same process. We get these other two species. All reactions are going to try to minimize the overall charge. Since our H plus is charged and the same in both cases, we can't make that comparison. So what we'll do instead is take a look at our other pieces. We get X minus versus Y. Which of those is less charged? Y. Okay, remember, charge can be both negative and positive. The only thing that's not charged is something that's neutral, so no charge. So when we take a look at that, we might predict that the starting material ends up being more acidic. Okay, and this is where some of this can get confusing. To determine the acidity of HX and HY plus, what are we looking at? So we could look at pH, but we haven't done that yet. We just said that HY plus was more acidic. Why did we say HY plus was more acidic? the charge where? Hydrogen we said was the same. We looked over at this species, our X minus and our Y. What is X minus and Y? Give me a name for those two compounds. It's a trickier question. They're in the reactant side or the product side? Product side, so they by definition would be conjugates. Okay? X minus and Y to go in the reverse direction. So this is how we would determine if it's an acid or a base. Okay? To go in this reverse direction, what must they both do? So as we move from X minus or Y over towards the left, what happened to those structures? They accepted a hydrogen ion, which means they acted as bases. So X minus and Y are the conjugate base of our acid. So if we're going to try and evaluate acid strengths, what we can do is look at the stability of the conjugate base. Okay? So it's kind of counterintuitive. You're jumping back and forth across this balanced equation and trying to determine our rank stabilities. Okay? So this is one of the first approximations that we can make. We can look at the overall charge. Okay? This example is a bit disingenuous. Okay? Why? Huh? It's not working? Is that what you said? What it? Oh, disingenuous. Our resident English major? Mr. Fickle? Disingenuous, meaning not a particularly nice example. It's not a very good one to look at. Okay. Is it just charge? What if we said it was chlorine? X and Y were both chlorine. Which is the more stable state? Chlorine minus or chlorine atom neutral? It's actually the ion. Okay? And that's because it's stable in that kind of salt form. So when we're looking at this example, it's not the easiest to decide what's happening with those charges. Particularly, we could jump back and say, okay, let's make this one X chloride, and we make this one, what's a good element that likes to be charged? Either nitrogen or oxygen. Okay. Our charge state really wants to actually hold those electrons. In our halogen row, it holds those electrons. Whereas if we move to a different position, it doesn't hold the electrons as well. Okay, so it can make that comparison difficult. When we're looking at comparing charges, what we want to do is make sure that our X and Y are the same thing, because those different elements can hold electrons in different fashions. Okay, so what do I mean? Well, what we can do is start to look at some other examples. Dang it. Okay, I wanted to swap the order on these. So when we go through and now pick specific examples, we want to try and decide where that charge should go. So if it gets rid of that hydrogen ion and it starts neutral as an acid, that negative charge is now going to sit on our conjugate base. What elements can hold that negative charge better? Or do all elements hold that negative charge the same effect? So for instance, let's take a look at two acids. Let's pick HF and water. Okay, what happens if we add these to water? We're going to assume they're reacting as acids, so what's our product for the first one? Don't look at the equilibrium. We're not evaluating that. We're assuming it acts as an acid. We get H plus and F minus. What happens in the other case? H plus and OH minus. Why'd you leave that other H on there? There's all sorts of fun answers we could give for this. That doesn't explain why we didn't write 2H plus O minus 2. So why is this now bottom one a bad idea? That's a valid answer. What's that? No. Nope, not even that. But that's also not a terrible one. What did we say was an acidic hydrogen? How did we look for an acid? What did it need to have? A hydrogen where? In front. So there's our first example. When we look at HOH, where's our acidic hydrogen? It's in front. That's the only acidic hydrogen in this case. Okay, so I set this up in that format that I was suggesting that you go through and look at. You don't always see it in that format, so we'd have to look for other things. Why else did we not go through in our red format? What did we say in our very first example of this when we looked at H plus or HX and HY plus? We wanted to do what? Minimize charge. So when you go through and look at this, both these reactions generate H plus. Which one has the more neutral charge? OH minus. Which one's going to be the more stable? OH minus. Turns out O minus 2 is ridiculously unstable. Okay? And we wouldn't generate that from water. So yet another reason why we don't see that reaction occur. Okay? So you can evaluate different levels to try and go through with these things. One other thing that we could add to it, when we said we're dealing with our acids and bases, what was our coefficients in most acid-base reactions? 1 all the way through. Okay, so yet another reason that we could say putting that 2 in front and taking it to O minus 2 is a bad idea. Okay? So that explains why we would go to OH minus. Now between these two, which of these is the stronger acid? You might be able to cheat with this. What's this species known as? Water. What's this species known as? Hydrofluoric acid. Which one's the stronger acid? Probably hydrofluoric acid. That's why we call it an acid. Why is hydrofluoric acid a stronger acid? Okay. What we're trying to do is always minimize that charge. So we go back to each of these species and we want to evaluate them. Where's the charge held? In our first case with HF, where's that negative charge sitting? We'll highlight the atom in each case. Where is it? Where's the negative charge? On fluoride. In OH minus, where's the negative charge? So we got to be careful with this one. It's on the oxygen. We could go through and add our lone pairs, and you would see it actually makes a lot more sense to put the negative charge closer to the oxygen than it does to the hydrogen. Okay. So when we go through and compare based on our first rule, both of these are negative, which means our first approximation doesn't help us. We need to come up with another rule, okay, or kind of an addendum to that rule, some modification. Okay, our overall arching rule is stable, or systems will always minimize that charge. Which atom can minimize the charge better, fluoride or oxygen? So we're seeing all sorts of answers. So oxygen, why do you say oxygen? Just a guess. Okay, why do you say fluoride? Fluoride is more electronegative than oxygen. What is electronegativity a measure of? How well an individual atom can hold bonding electrons. Okay? Fluoride takes the bonding electrons away from our hydrogen more easily than the oxygen, which means this fluoride is going to hold those bonding electrons better than the oxygen, which means what happens with the reverse reaction? Happens less frequently, which then means HF ends up being the stronger acid in that pair. Okay, kind of get the relationship there? So as far as what you need to be able to do with this, okay, you can go through and reason your way through it all the way through, all the way back to our basic principles. Or we can go back to what I've labeled as rule number 1, which is, I think how your textbook shows it, but I prefer a different order. I should have fixed it. Across a row. So if we're comparing our conjugate base atoms where the negative charge is held, okay, the stronger acid will have the higher electronegativity. So when we compare HF and technically HO in this case, okay, the atom that holds the negative charge is fluoride or oxygen. Where are they on the periodic table? In the same row. So we can compare based on electronegativity in this case. Okay? Is it yawning because this is too easy or too early? I guess we'll run with too early. Okay? Questions about that comparison? Okay, so let's propagate this out a little bit differently. Now let's go through, let's stick with HF because I like HF. Actually, they don't, but we don't need to like it for this. Let's switch to HCl. Goes to H plus and Cl minus. Which atom holds the negative charge in HCl? Cl. Just checking. Okay. So the first thing we'll do is go back to our basic principles, because you all memorized your 6 strong acids. Which of these 2 acids is the strongest? HCl. Well, how do you know that? Because it's a strong acid. It's one of those ones you memorized. Is HF on that list? No. What does that mean? HCl, by definition, is a stronger acid than HF. Okay? Now we've got to come up with an explanation for this. If we go back to rule number 1, we said stronger acids have a higher electronegativity. Go to your periodic table. Which element has a higher electronegativity? Fluoride or chloride? See how many of you remember your trends. Fluoride. Electronegativity increases across a row and up a column. Fluoride is the most electronegative element on our periodic table. Okay? So according to what we've interpreted from rule number 1, at least the end part of this, we would say HF is the stronger acid, and we are proven wrong. What does that mean? It's not so much that there's an exception, we have to apply a different rule. Okay? Our initial assumption was just across or higher electronegativity. Okay? And when we go through and looked at our comparisons, we could say HF versus HO, our HF is a stronger acid. In that comparison, they were in the same row. Let's take a look at fluoride and fluorine and chlorine. Where are they in the periodic table? Not in the same row. They're in the same column. So what changes when we move from the row to a column? Electronegativity definitely changes, but it goes down. So that's counterintuitive to our transitioning. What else changes as we go down a column? It becomes more acidic. Don't use polarizability. Mass, size, and orbitals are all good answers on this. As we continue through the periodic table, we start to add what? More electrons. As we shift down our rows, right, down the rows, so within a column, okay, we're going up to a larger energy cell, which means the electrons get further and further away from the nucleus, which means our atom size gets bigger. How is that going to affect our overall charge? Okay, so what we can do here is do some comparisons. I'm going to draw a picture of fluoride and chloride because I'm a really good artist. Okay, here's our fluoride. Don't laugh, come on. That was serious. I am a good artist. I was kidding. God, too early. There's fluoride. I said I was a good artist, right? And fluoride, because it's negatively charged, has what extra thing floating around in it? An electron. So I'm going to be a really good artist and draw my electron. Ta-da, there's my electron. Can you guys see that, or is that too small? Okay, so we've got the larger circle representing the fluoride atom and the small little dot inside representing the electron. What happens when I get to chloride? It gets bigger. Okay, it gets actually substantially bigger. So let's draw chloride. Okay. Does the electron get bigger? No, it's the exact same size. Let's go ahead and draw that little electron dot back in there. Okay. How does this help? Yeah, that's what you should be asking me, right? Okay, well, what's bad about each of these structures? Both fluoride and chloride. When we look at those, we immediately say, okay, something's unstable with those. What's that thing? They're charged. They have that extra electron in there. So charge is inherently bad. That's why when we stick our fingers in the electrical outlet, it hurts. Okay, which is why you don't do that. So don't do that. Okay? What's coming out of the electrical outlet? Electricity or electrons. So here we go. We look at each of these structures. If you touch the electron, you get zapped. Okay? Hurts a lot. Okay? Now I force you to stick your hand into one of these atoms. Which atom do you stick your hand into? The bigger one. Why? Less likely to touch the electron. What does that mean about the stability of the electron? It's more stable. If the electron's more stable in chloride, what does that mean about the stability of fluoride versus chloride? Chloride's more stable. If chloride's more stable, is it willing to give the electrons back to hydrogen to go in the reverse direction? No. What does that mean about the acidity of HCl versus HF? It's the stronger acid. Okay? Now I'll get you. What was your question? You got it now? Oh, okay. Kind of makes sense? So let's put some words to that rule, in case you don't want to derive it. Down a column, your stronger acids are larger. So the larger the atom is where your negative charge is held, the more acidic it becomes. Okay? After that, your rules start to get all sorts of wonky. Okay? And in fact, I don't actually remember these two rules, the next two. So I'm going to have to look cheap and see what the rules were. Okay? When you move into organic chemistry, these are the first two rules that you're going to deal with. So these are going to be the primary rules that you're going to get tested on this semester. You will probably see multiple questions based on these two. Okay? So let's come up with another way that we can test on it. Let's make this really fun. Let's go through you don't have to be familiar with all of the notation, but hopefully the important parts you'll see. Which hydrogen is the most acidic? So if that's the question, what do you need to do? First thing, we're looking for the most acidic thing. What do we need to be looking for? Find a hydrogen. Good call. Okay, where are our hydrogens? We've got one to oxygen. We have two to nitrogen. Should we evaluate both those hydrogens? No, why only one? They're effectively the same thing. They're both attached to a nitrogen atom. So let's just look at one of those. And anything else? Carbon. What about the rest of all of that stuff out there? Actually, let's not quite do that yet. Okay, to figure out if they're acidic, we need to see what that hydrogen is attached to. So we could now evaluate our bonds to see what they're attached to. What about the rest of all those lines? Why are they there? Kind of a mean reason. Because it's going to confuse you and you're now going to think this problem is ridiculously difficult. That's it. Okay? The rest of that is extraneous information, completely irrelevant to the problem. Okay, at least at this case, yes.
Including the other hydrogen on the nitrogen?
Including the other hydrogen on the nitrogen. Okay? So what we would now have to do is evaluate each of these. Okay, and we can do it a couple ways. One, we could go through and look at the conjugate base for each of these. Okay, and since I don't want to draw it out 3 more times, if we look at the conjugate base up here, what are we going to get? H plus and O minus attached to a bunch of junk. I don't care what bunch of junk is. That's all it is. What's the next one? Bunch of junk. Last one. H plus and C minus with a bunch of junk. Okay, so we could draw that out. Now what would we do? We would go through and look at those 3 atoms. Where are negative charges? Look at the stability of the conjugate base. Okay? I heard someone say electronegativity. I don't quite want you to say that quite yet. What do I want you to look for first? Good call on looking for the minus charge. We should evaluate to make sure they're all negative. They are all negative, so we can't evaluate that. Where they are on the periodic table. What is the relationship between these 3 elements? They're all in the same row. Since we know they're all in the same row, the stronger acid is more electronegative. Which atom is more electronegative? Oxygen. Which one's the next most acidic? Nitrogen. The last one, I guess, carbon. Okay? So break it down into the individual pieces. Only evaluate the parts that are important. Okay? Would I give you this structure without drawing on the hydrogens? No, because that's just really mean. You haven't learned officially how to draw organic structures, so I'm not going to assume that you know what all of those individual pieces mean. Okay? As far as I'm concerned, I could draw a T-Rex and then have a carbon and a hydrogen coming off of it. Okay? Or as far as you're concerned, that could show up on the test. Okay? All you're doing is evaluating that acidic hydrogen. Okay? Make sense? Okay. Okay, so the next big rule that the textbook thinks is important to memorize. HOX becomes more acidic with a higher X electronegativity. Okay, so let's look at an example here. So what we're saying is if we take HO, and let's make this a chlorine, versus HO, that's pretty boring. Let's go to iodine. Okay, if we're going to assume these are acids, which is a pretty good assumption in this case, what do our products look like? First product, both of these would be H plus. What's the other product? Heard it there. OCl. Where's our negative charge held? Why is it on the oxygen, not the chlorine? So we can introduce a little bit of organic here. Draw this real quickly. We'll do OI for the other one. Our negative charge does sit on the oxygen in both these cases. If we draw on our lone pairs, we could add those on. Why does it go to that oxygen? Well, what are the electrons? Where are the electrons that make that hydrogen-oxygen bond? Okay, we drew out our Lewis structure effectively here. Where are those electrons? Where are the electrons that make this hydrogen-oxygen bond? Can't tell me on the oxygen because then there wouldn't be a bond. How do we get a bond? Sharing of electrons. Where are those electrons represented? the line in between. What does that line represent? Represents 2 electrons. If we go down to the other one, there's too many there's. There. Okay? If we're going to make this an acid, H plus has to come off, which means how many electrons does this H plus have? Hydrogen atom has how many electrons? 1. If we make it positive, how many electrons does it have? 0. Where did that electron go? Why do we go to the oxygen, not to the chlorine? Chlorine is too far away. How stable are electrons? Not stable at all. They go very, very short distances. We cannot pull them off and move them through space easily. Okay, which means those electrons are going to go as short as possible and sit directly on the oxygen. If we were going to go through and show them in red, we could show them as now a lone pair on these. Okay? And if, just because it's fun, we wanted to show mechanistically, so show how the electrons moved. Where did the electrons start? In the bond, right? Between those 2 atoms. Where did they go to? The oxygen. How would we show the motion of something? We'll use an arrow. So we will take an arrow and say the electrons started in our bond and moved towards the oxygen. Your first lesson in organic chemistry. There it is. Okay, we use the arrow to show the motion of those electrons. Okay, let's get back to ranking these as far as acidity goes. So we look for charge. We look at our conjugate bases. Are the charges the same? Yes, negative and negative for our conjugate bases. Go ahead and box those in so you can make sure we're, whoa, so we can compare that better. What's our next rule? Across a row, the stronger acids have higher electronegativity. When we're doing that comparison, what are we comparing? What 2 things do we compare when we're looking at rule 1 or 2 or 3 or any of these rules? The atom that has the negative charge. In both these cases, what's the atom? Oxygen. Is there a difference between oxygen atom and oxygen atom? No. How useful is rule 1? Not. Move to rule 2. What does rule 2 say? Down a column. Look where the charge is held. Where is it on? Or what atom is it on? Oxygen. Is there a difference in size between oxygen and oxygen? No. All of our rules so far have become useless. We can move to rule number 3. Rule number 3 says if X or X becomes more electronegative, we get a stronger acid. What's the more electronegative element here? F or C? Or, sorry, Cl or I? Cl. Which one's the stronger acid? HOCl. Okay. Why does it become a stronger acid? Higher electronegativity, fair enough. Why does increasing the electronegativity make it a stronger acid? That charge is not on the chlorine. What is electronegativity a measure of? It's not stability, it's a measure of attracting, more specific, it's not just electrons, bonding electrons. Where's the bond to this chlorine and to this iodine? To the oxygen. If we say chlorine is more electronegative than iodine, what happens? It starts to take those electrons away from oxygen. What happens to the oxygen now? It starts to become positive. It goes, oh crap, I'm losing electrons. So what does it do? Pulls them completely away from the hydrogen. And it does not share them back. We don't see the reverse reaction as much. Okay? So what we're doing is propagating our rules further through the structure. We look first to see where our charge is, if we can get a comparison between our charge. We can then look to see what atom we have. Okay? If we're within a row, so we're looking at atom effects. Okay? Our atom either is larger or it has a different or more electronegative. Okay? After that, we have to propagate our issue or our problem even further away from our charge. Ultimately, all of these were evaluating that charge. We started at charge, then we moved to atom. Still no effect, what do? We move to the bond. Okay? What affects that bond? Well, the other atom that's attached to it. Okay? Does that kind of make sense? Okay? Guess what we're going to do on the next one? Yes?
In the last scenario when we had fluorine and chlorine, we said that the chlorine won.
Yes.
Because it got bigger as you moved down.
Yes.
Well, in this case, iodine.
Where was the charge held in that last case?
On those elements.
On the chlorine versus the fluorine. Okay? And in that case, chlorine can stabilize that negative charge better. Okay? So it's an atom effect. When we move to this next example, where's our negative charge held? Oxygen. Okay? So we can't go to that size effect because there is no size effect between oxygen and oxygen. So now we move to the bond, the next thing furthest away. We want to take a look at those electrons and what things are affecting those electrons. Okay? Are they stuck in that bond or are they being pulled further away? The only way we can evaluate that is electronegativity. Size doesn't have an impact. Well, it actually has a counterintuitive impact there, but we don't have to worry about that. Our electronegativity is pulling the bonding electrons away. That oxygen starts to panic, it needs to grab electrons, it'll take them from the hydrogen. And so we end up generating a stronger acid. Okay? So this is why these rules can become difficult, because it's at what tier are you evaluating? Start at the charge, move to the atom. Still no difference, move to the bond. So the very next thing, that's that bond. Okay, what we've got highlighted in blue. I guess I should have highlighted it in green, because that's where our comparison is. Okay? In this case, we are now comparing that bond. What affects that bond is the electronegativity of the next atom. Okay?
Because you asked that question out of curiosity for the memorization of the acids, did you put them in a particular order that one's stronger than the other, or no? Because you're saying that hydrochloric.
Oh, for the strong acids? I don't think I put them in a particular order.
Okay.
On that list. You should be able to go through and do that. If we compare, and we actually already did this comparison, HI to HCl, which one's the stronger acid? They're both stronger or strong acids. Look at the conjugate base. Where's the charge held? Chloride versus iodide. Where are they on your periodic table? They're within a column. Which rule can we use? Rule 2, which atom is larger, iodide or chloride? Iodide. Which one's the stronger acid? HI, or hydroiodic acid. Okay? So we can still use these rules to even put rankings within our strong acids.
Okay.
But I don't think I ranked them necessarily on the slide. Yeah. Okay? Clear as mud? So, next comparison. Let's go through and change our structure again. Which one's the stronger acid now? What was that answer?
Is that a chlorine?
Fair enough. Yes, that's chlorine. Good. Just checking. They're the same, so now let's make one more little difference here. With this bottom chlorine, kind of out of space, but we'll do that. And for those of you that think I'm over teaching this, just so you know, this is totally something you're responsible for this class. I'm not making it up entirely. Which one's the stronger acid now? Why the bottom? Let's go through and evaluate, starting at the beginning. Charge. Is there a difference on where the charge is held? No, or the same charge. Atom. Oxygen versus oxygen. So same electronegativity, same size, no difference. So the next thing we would do is move to the bond. Okay, what's the bond next to that oxygen? Chlorine versus chlorine. Is there a difference? No. So what do we do now? Move to the next bond. Okay, when we move to the next bond, what's the next bond on this top chlorine? Nothing. Okay, which means it's pretty happy with its electron cloud. When we move to the next bond down here, what do we see? Oxygen. In fact, we see two oxygens. What are those oxygens, or a particular characteristic of oxygen? It's electronegative. It's the second highest electronegativity. What's up?
Shouldn't that have a negative charge that oxygen is pointing at?
I was leaving that off intentionally.
Oh,
Yeah. We don't need to balance that necessarily. Okay. Oxygen is extremely electronegative, more so than chlorine. What does that mean? What does it do to the electrons in that bond? It pulls them. If it takes electrons away from the chlorine, what happens to the chlorine? It needs electrons, so where does it get them from? Its bond. This oxygen now gets pissed and says what? It takes the electrons away from the hydrogen. Which one's the stronger acid? The bottom one. Okay? For a relatively similar reason as rule number 3. We just had to propagate that rule out another bond away. Okay? So we can star that. Our bottom one is our stronger acid. What's the rule and why I actually skipped off the negative here? Rule 4. HOXO to the N number becomes more acidic with more oxygen. So the larger that N number becomes, the more acidic it becomes. Okay. N bigger. Equals more acidic. So as far as leaving off that charge that Victor was talking about, I'm not going to expect you to know structures and ultimately where all those charges are held in your Lewis structure. What I do expect you to know is the overall formula rule. Okay, but I wanted to be able to see those bonds. Without those bonds, it becomes just a rule to memorize. Okay? Questions about that? Okay. So as far as being able to...
Does that apply with other elements as well? Besides
other electronegative elements, yes, it does apply to other things. You'll see those other things in different classes. As far as what you are responsible for with the rule 3 and 4, we're only looking at X being a halogen in both 3 and 4. And in rule 4, we're only looking at oxygens being tacked onto our halogen. Okay. We could look at one example that's outside of the class, which we'll look at in just a second. Let's hit some questions first.
so rule 4 would be a stronger acid than rule 1 compared to 3?
Yeah, careful with that. So which rule do you apply? Okay. So he said rule 4 makes it a stronger acid than rule 1. You have to compare in sequence. The very first place we start is with charge. The next place is where the charge is held, which is rule 1 and 2 on our atom. The next place is the bond after that. The next place is the bond after that. What's rule 5? The bond after that. Rule 6. Bond after that. And so on and so forth. So when we're looking at ranking these acids and bases, when I went through and did the comparisons, I only looked within an individual rule because we're slowly stepping further and further away. So when you go through and rank your acids and bases, which is kind of where I was going to go to next, how would I ask questions? I would ask you to rank within an individual rule set. Okay? Because it's very difficult to cross those rules over and still be able to rank them appropriately. It's a more advanced question. You might see that in organic chemistry. We'll stick within a rule. I won't tell you which rule. You'll have to decide that, but you should be able to see it from the structures.
I guess it's just kind of along the same lines as that. So like on a rule 2 with chlorine and fluorine, the chlorine is more acidic, but say the fluorine had an oxygen on it.
You would look at the atom. So you still go based on that atom
Based on
charge.
the negative, the one
Yep, where the negative charge is held. It's actually kind of interesting in that respect. Fluorine wouldn't have an oxygen on it, just so you know, but yeah.
Is oxygen the only element that these rules apply to?
It needs to be an electronegative element. The only other electronegative element would be something like fluorine. So we can propagate or apply these rules to other situations, but those other situations would pop up in organic chemistry. You won't see them here. Okay? And since we're seeing a lot of those questions, we can come up with a couple quick examples on that. So those two verses, and just to be kind of a jerk on this, those two verses. Stronger acid in the blue pair would be left or right? Why left? Where's the acidic hydrogen first off? It's kind of nice in this case. Okay, it's the far right. Whoops, let me highlight there. For that one, with the next one, still the far right, it's the one attached to the oxygen. When we compare those two, our conjugate base, where's the negative charge held? Oxygen. No atom size difference, no atom electronegativity difference. So we move to our next rules. Our next rule becomes more acidic with higher electronegative elements attached. Okay, so we go out to atom X. Atom X in this case would be carbon. It's the same, so doesn't apply. Rule 4. Increase the number of oxygens, what happens? Becomes more acidic. Which one's more acidic? The left one. Functional groups. We just circled a functional group known as a, you'll definitely learn this with the next lab, a carboxylic acid. What's the other one? Alcohol. Which one do you think is the acid? The one that we call an acid. Okay. When we move to the red example on the right, a little bit trickier. Where's our acidic atom? Which hydrogen on the carbon? So let's pick the one on the right first. Maybe that one's a little bit easier. Where's our acidic hydrogen? The only one that's on it. Okay, that works. How about the one on the left? Doesn't matter. Why does it not matter? They're all the same, so we won't worry about that. Let's just box one at random. Okay, go back to our rules. What would our conjugate base be? You don't have to give me a complete formula. Be carbon negative, right, in both cases. Okay. Carbon atom, different electronegativity from a carbon atom? No, rule 1 sucks. Rule 2 also doesn't work. So rule 3. Right, this one's a little bit weird because when we looked at rule 3 initially, we included that oxygen atom there. Except now our oxygen is actually a carbon. So what happens as we add an electronegative element to our atom? We increase the acidity. Which of these two is more acidic? The right one. okay, because of more electronegative elements on it. So we do apply these rules very, very similarly when we move into organic chemistry. They do come through the same idea. We call them different things. We look at resonance or inductive effects. You aren't responsible for those terms, but they do contribute to this. Okay? So having a firm understanding of these rules can get you through 90% of organic chemistry. Okay? Where it's probably 100% of first semester and 50% of second semester. That averages to 90, right? Okay. Questions about it? Oh, sorry, yes?
So if you figure it out in the first roll, you're done?
Yep.
You don't have to go through all of them?
Yep, there's no point in continuing through it if you already know your answer at rule 1. So we would apply in that sequence. Start with your charge, okay? Then move to your atom effects, which would be rule 1 and 2. Then move to rule number 3 if you still haven't found an effect. So it's always go slowly, stepwise. Find the difference first. Once you've found that difference, then you can apply your rules. Okay? Yes?
Going back to prior to rule 1 when you had the X and the Y,
Charges, yep.
you were talking about how Y being neutral compared to X being negative charge.
Yep.
Being stronger. What happens if you have a Y positive?
If you had a Y positive, you started at a +2. You're going from +2 to plus. That's a pretty big transition. You're definitely getting more neutral in that effect. But yeah, you might run into some gray areas there.
Okay.
Okay. Other questions? So what we went through and did is derive these rules. You can either derive them on your test or you can have them memorized. I don't care which you do. Okay. But it is something that you absolutely will get directly tested on. Okay, so we can kind of crunch out some math now. Let's determine the concentration of hydronium and hydroxide ion in a 0.15 molar HF solution. Decided to be a little bit mean. The pKa for HF is 3.16. Okay, I'll let you guys go ahead and get started on this.